Similar and congruent triangles. Our learning goal today is to determine if triangles are congruent or similar and solve problems that are related. Please ensure you have the lesson printout so you can follow along with this video. Before we get started on similar and congruent triangles, let's first look at some general labeling guidelines for triangles. The first thing we'll notice is that the vertices or corners are labeled with capital letters. For example, this triangle could be labeled capital A, B, and C. The side lengths can be labeled in two different ways, as a lowercase letter of the opposite vertex. For example, this side between B and C here, since it's opposite A, you would give it the lowercase a. Likewise, this side here, because it's opposite angle C or it's corner C, we'd call it little c. And likewise, little b would be over here. So this is referring to the lengths of these sides. It could also be referred in another way. So if we're talking about the length, we could just say it's the distance between B and C. And over here, it will be the distance between A and C. And here, it would be the distance between A and B. So those are two different ways we could label it. So this is A and B, for example, is a way to measure the distance between corner A and corner B. To label angles, we use the angle symbol. It looks like this slanted L, followed by a letter of the vertex being referenced. For example, if you wanted to label angle A over here, we would call it angle A. Of this lesson, we're going to be using this second version of the side lengths, but we'll return back to the first version here in a later lesson. Types of triangles. Pairs of triangles may be congruent, similar, or neither. The order of the letters naming the vertices of congruent or similar triangles indicates the order in which the vertices, sides, and angles of one triangle correspond, or in other words, are related to the vertices, sides, and angles of the other. Let's first look at congruent triangles. Congruent triangles are identical in every way. They have the exact same shape and size. They may be rotated and flipped or mirrored into a new position. Let's take a look at some congruent triangles. Take a look at triangle ABC and XYZ. If we were to measure these sides, we would see that side A and C is equal to side X and Z. Side A and B is equal to side X and Y. And side B and C is equal to side Y and Z. Similarly, if we looked at angle A, it would be equal to angle X. Angle C is equal to angle Z. Angle B is equal to angle Y. So we can see that these triangles are exactly the same in length for their sides and for the angles that they have. So the way we'd write this is that triangle ABC is equal, and there's this little symbol that we're going to write on top, which means congruent, to triangle XYZ. This means that triangle ABC is congruent to triangle XYZ. let's take a look at similar triangles. In similar triangles, the triangles have the same shape, but are different sizes. One triangle is a larger or smaller version of the other. So taking a look at this example here, we can see two different triangles, but where triangle ABC is similar to triangle XYZ. But what makes them similar? You clearly see the side lengths are different, but the angles are the same. So this is what makes them similar. We know angle A and angle X are actually the same angle. We can see angle C and angle Z are also the same angle. And angle B and angle Y, again, the same. Looking at this, we can see, because we've matched up our angles here, we can see that certain sides are related to each other. So if we wanted to see the proportions, what we can do is look at how much bigger the big side is compared to the small one. So we can think of the distance between A and C, and we want to divide it between the similar side, X and Z. And if we found this, you would get the ratio between the two. And imagine it's 2 to 1, so it could be 2. Right? It could be like 2 over 1, for example, which is just equal to 2. Which is saying that the big side is twice the little one. Okay, if we check A and B, we can check the other side, which is X and Y, and we'll see that it'll be the same value when we find the ratio. And last one, B and C and X and Z. So B and C, X and Z, and if we check this, it should also be 2, since the rest of them are 2. That's when we know that the triangles are similar. So they have the same angles, but they're all proportional to each other, the sides. So we can say triangle ABC is similar to triangle XYZ. This means, in words, that ABC is similar to triangle XYZ. So just one thing to point out, this corresponding sides are proportional, the ratio between these two, the scale here, has a specific name. We call this the scale factor. It tells us how many times bigger or smaller our triangles compared to the other triangle. For me, I like to stay consistent, and I usually always put the big triangle on top, or the values of the big triangle on top, and divide it by the values of the little triangle at the bottom. As I've done up in here. We're going to use this idea to solve 4 different problems. The scale factor for congruent triangles, if we were to measure the distance between C and B and Y and Z, for example, we'd see if we put C over B divided by Y over Z, our scale factor here, because they're exactly the same, is going to be 1. Okay, so that'd be the scale factor here. So the scale factor for any congruent triangle is always 1. So let's summarize. The scale factor is the value of the ratio of corresponding side lengths in a pair of similar figures. Let's try putting all this information together so we can answer problems. Example 1. Name the similar triangles. Write the letters so that the equal angles appear in corresponding order. So here we can see we have two different triangles. We're not given any information on the side lengths. So at this point, we can only conclude that the triangles are similar. If you look at angle A, from vertex A, we can see that this angle matches up with Q in our other triangle. Okay, so from this triangle, we'll say triangle, the A matches up with the Q. If we look at angle B here, that matches up with angle R. And angle C matches up with angle P. So triangle ABC is similar to triangle QRP. Again, the idea is just to match up the angles with each other in the same order. So just remember that the squiggly line here means similar to. Let's try another example. Example 2. Is triangle DEF similar to triangle ABC? Angle C and angle E are corresponding angles in the two triangles. So you can see angle C here and angle E here are the same angles. If the triangles are similar, then their corresponding sides should be proportional. So let's take a look at the proportions or the scale factors of each of these triangles. As I like to do, I always like to put the big scale factor over the little scale factor. For example, let's take a look. We will compare side A and C to side D and E. So we're going to put the big triangle over the little triangle. So we're going to compare A over A and C, so this side here, to D and E. So that's going to be 2.4 over 1.2. And we're going to get a scale factor of 2. Now let's check from C to B and E to F here. And if they're similar, they should have the same scale factor all around. So C over B, or C to B, sorry, to E to F. On this triangle, we're going to get 3.7 over 1.5. I think you'd already see that this is not the same. This is going to be 2.47. Because the scale factor is not the same everywhere, the triangles are not similar. So we can conclude triangle ABC is not similar to triangle DEF. Okay, so they're not similar. Example 3. Determine the unknown measures. Here we're going to use scale factor to determine the length of the missing side. The first thing that we need to do is to determine our similar angles. We can see this X pattern here. Whenever we see that, we know that this angle is equal to this angle over here. This angle here will be equal to this angle over here. And this angle here is going to be equal to this angle here. So now we kind of labeled all our angles and we have a good bearing of where we should be. we know that this side here is going to be similar to this side here. This side here is going to be similar to this side here. And this side here is going to be similar to this side here. So now we can compare these scale lengths. So let's compare the similar sides. We know two of these measures here for each of these triangles. We know this measure here, B to C, and we know this measure here, C to E. So let's compare them. The way I always like to do this is I like to put the big triangle ratio over the little triangle. So let's say big triangle over little triangle. And what I mean by that, we're going to put the big value here, BC, over the similar C and E. And this will be equal to our scale length. So let's find out what that is. So B to C, that's 6, and C to E, that is 4. And this will give us a scale length of 1.5. Now, this scale length is going to be the same for both of these triangles. So we know, what are we missing here? We're missing this big measure here. So remember, it's big over small, so we're missing X, which is big, and over small, which we know is 3 centimeters. Okay, similar to this. So this is equal to A to B, and this is D to E. And this ratio here should also be equal to 1.5. So we can solve this. We have X over 3 is equal to 1.5. So we just need to solve for what this is. And to do that, we're just going to multiply 3 on both sides. So these are going to cancel. We're going to get X is equal to 1.5 times 3. So therefore, X is equal to 4.5. So we know that this value here is 4.5. Let's try example B. The first thing we need to do, as with all these questions, is to identify where the similar angles are. There's actually 2 triangles here, and I'll highlight it just to make it look a little bit clearer. We have one right over here. Okay, so what angles do we know? We know angle P here is going to be the same as angle M over here. We know angle N over here is going to be the same as angle Q, and angle L is shared between both these triangles. So we know the big triangle over here, one of the side lengths is going to be L to P. And if we want to compare it to the smaller triangle within it, it's going to be L to M. We can compare this to the other side. So the big triangle on this side is going to be L to Q. And on the little side, it's going to be L to N. So the proportion between LP to LM is going to be equal to LQ to LN. And so we could fill in these numbers. So we know from L to P, that's 15 plus 5, so that's 20 centimeters. So that's this total distance here. We know L to M is just this distance here, which is 15 centimeters. L to Q, we're not sure what that is, but we know it's going to be X plus 4. So we have this distance here is X plus 4. And between L to N is just X. So now we have our ratio set up. We can start solving. To solve this ratio, we could use the following method. We can cross multiply our denominators. So if we multiply this to the top here and this to the top here, it'll cancel them on the bottom. So let's go ahead and do that. We have 20 times X is equal to 15 times X plus 4. And we could expand it and simplify. So it's going to be 20x is equal to 15x, and 15 times 4 is 60. So let's solve for what x is. Let's move all the x's to one side. We're going to move this over here. So we're going to get 20x minus 15x is equal to 60. 20 minus 15 is going to be 5x is equal to 60. And let's just finish this off over here. We have 5x is equal to 60. To get x by itself, we'll divide both sides by 5. These are going to cancel. We're going to get 60 divided by 5. So x is 60 divided by 5, which is 12. So we know the distance from here to here is actually just 12 centimeters. Example 4. Find the value of each indicated quantity. So we're missing this side here. We know that this here is going to be the same here, and vertex C for both of these. So this angle here is going to be the same as this angle here. I'll just the double angle to indicate that one. And then we have 90 degrees in the corner. So we're missing x. We don't know what x is, and we want to find it. We do know two ratios here, or two sides that we could use to find our ratio. We know b to c is equal to 12, and we know c to d, the corresponding side on a smaller triangle, here is 3 centimeters. So we know b to c over c to d will be equal in proportion to a to b and to e to d. So what do we know here? We know b to c is 12 centimeters. We know c to d is 3. And this is equal to a to b, which we don't know, which is x, and e to d, which is 7. So for this question here, we can implement the same thing that we did last time and multiply the denominators to each side here to solve. So 12 times 7 is equal to 3 times x. And if we did that, 12 times 7 is 84 is equal to 3 times x, which is 3x. And now we can solve for what x is by dividing both sides by 3. So 3's are going to cancel. We're going to get x is equal to 84 divided by 3, which is 28. So our missing side here is equal to 28. Let's try one more example. Romeo uses a mirror to determine the height of Juliet's window. He knows when light is reflected from a mirror, it makes the same angle on both sides of the point where it strikes the mirror. The angle of incidence is equal to the angle of reflection. How high is the window from the ground? So this uses the same principle that we learned in optics. So this angle here is going to be the same as this angle right over here. We know this angle is 90 degrees, and this angle here is the same. So we can see how we have our two similar triangles. So what do we know? We know the big triangle here, the distance between the mirror and Juliet's house is 5 meters. And we know that's similar to the distance between here and here, which is 0.5 meters. We don't know the height of the window. We'll call it x. So that's on our big triangle. And our little triangle, we know the similar height is 1.6. So we're going to get something set up that looks like this. So again, this is big triangle side, so we know the 5 meters over the little triangle similar side, which is a little triangle, and this is the big triangle here. We don't know what the x is. And this is the little triangle here. Okay, so now we can go ahead and solve for what x is. we have 5 over 0.5 is equal to x over 1.6. We can use the same technique that we've been using. So we're just going to cross multiply. So we're going to get 5 times 1.6 is equal to 0.5 times x. So let's simplify. Bring that right over here. 5 times 1.6 is 8. Is equal to 0.5x. And to get rid of x, we're just going to divide 0.5 out on both sides. These are going to cancel. 8 divided by 0.5 is 16. So therefore, x is equal to 16. So we know Joliet's window is 16 meters from the ground. And so that's it for our lesson for today. And this is our first lesson in trigonometry. And so hopefully it's not too bad. We're just going to be learning a lot from triangles.